All right, so we can do this with O2 and other, more complicated atoms. Typically, we just do n equals 1 and n equals 2 from the periodic table. But let's figure this out. So I've already drawn the MO diagram, right? So 1s has come together to give me a sigma bonding MO, so sigma 1s, and a sigma, it's going to get a little crowded, sorry, sigma star 1s. 2s atomic orbitals come to give me a sigma 2s and a sigma star 2s. The p's, I have 3 p's, so now I need to get the same number of, I have 6 p's total, so I should get 6 MOs. And they can come together this way. If my x's come together like this, I get a sigma 2p MO. If they come together like this or like this, I get my pi. So these are pi. This one I suppose will be pi 2p, and this will be pi 2, or 2py and 2pz. Here now, so this is my non-bonding energy line. So my pi's are here, so my pi stars should be here, pi star 2py, pi star 2pz. Sigma bonding MO is lower energy than my pi, so the anti-bonding should be higher energy than the pi. Sigma star 2px. All right, there we have it. So there's the labeled MO diagram. Now we have to put the electrons in. So again, I'm not even going to worry about putting the electrons on the outside. I don't want to put them in the AOs. They're just going to confuse things. I'm only interested in how many total electrons. So O, are we doing everything? Yep, 1s, 2s, so not just valence, but all the electrons. O has 8 total electrons. So O2 should have 16 electrons. And I just put them in from lowest to highest. So 2, 4, 6, 8, 10, 12. Oh, I'm breaking the rule. 12, 14, 16. I kind of broke Hunt's rule while I was writing there, but you can't tell now. All right, so I've got 2, 4, 6, 8, 10, 12, 14, 16 electrons. Check. All right, now we can do some calculations. So the first thing we can look at is the bond order. So bond order equals the number of bonding electrons minus anti-bonding. So 2, 4, 6, 8, 10. 10 bonding electrons minus 2, 4, 6 divided by 2 equals 4 over 2 equals 2, a bond order of 2. And this is actually what we expected, right? Lewis structures predict a double bond, a bond order of 2. Nice. Let's just look at this. So here's a shortcut to think about. We'll go back. I can count all of the bonding electrons, or what I know is if I have a full MO, the sigma and the sigma star are both full, these guys are going to cancel each other out, so I can ignore them, right? So when I can't calculate my bond order, I could just do the ones that aren't complete. So how many bonding electrons do I have here? 2, 4, 6 minus 2 divided by 2 equals 2 equals 2. You get the same answer. So you can use all of the electrons or just the ones in the incomplete MOs to do that. All right, so we predict that oxygen should be stable, right? It should have double bond character. And the last thing we can figure out is it diamagnetic or paramagnetic? And we just solved our issue. Why is dioxygen paramagnetic instead of diamagnetic, right? The MO diagram shows that these electrons and these pi star 2p orbitals, they're separate. There's one in each. So oxygen is paramagnetic. Nice work by us. All right, so look here. It was sigma first and then pi. And this is what I expect. When I have overlap of orbitals coming directly to each other in a sigma bond, that's better overlap than the pi. And so I expect the sigma bond to be more stable than the pi. So this makes sense to me. Let's do the next one, and we'll see that it's not always true. So we're going to do B2. I've already drawn the MOs for you. Let's label them up, though. Let's get the black pen back. Hold on. All right, so AO is coming together. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Whoa, something's different. Pi first, then sigma. That's the opposite from what we saw with oxygen. I expect sigma to come first, be lower energy, more stable than pi. But what we see is for B2, and it turns out these guys, it's reversed. And it has to do with something called orbital mixing, and I'll do some hand waving and talking in a second. So we get the pi to p, or z, sorry, and pi to py. This will be a sigma to px. Note that the pi up here, right, and the sigma remain the same. So it's the only change is happening right in here. And it mostly has to do with this sigma. So this will be sigma pi star to pz, pi star to py, and sigma star to px. All right, all labeled up. Now we're going to put our electrons in. So we're doing all of electrons. So how many total electrons does boron have? Each boron has 5 electrons. So diboron should have 10 electrons. No cations or anions, so I just fill them up from the bottom. 2, 4, 6, 8, 10. There we go. That is the MO diagram for diboron. And 2 things we can calculate is, well, first off, is it diamagnetic or paramagnetic? You have unpaired electrons, so it's paramagnetic. And the bond order is going to be, bonding is, let's see, I'm going to count them all, 2, 4, 6. 6 minus 2, 4, divided by 2 equals 2 over 2 equals 1. Shortcut, ignore these guys. 2 minus 0 over 2 equals 1. Regardless, bond order is 1. So we expect, or molecular orbital theory predicts, that diboron, boron held together by a single bond, should exist. All right, let's have a think about what's going on here. Remember, when we were putting electrons around atoms, for the hydrogen atom, where we have the electron configuration, we start from 1s, then 2s, 2p. For hydrogen, the energy depended only on n. All n equals 2 had the same energy. All n equals 3 had the same energy. They were degenerate, right? And that's how we could calculate the energy using the Rydberg equation, What happened when we had more than one electron? We start putting electrons in there, those things, and what we saw is that the energies changed. Remember the electron configuration for copper? It is argon, and then 4s. So we expected it to be 4s2, 3d9, but remember it was really 4s1, 3d10, right? Nature likes that fully filled d subshell. It was a stabilizing effect. So by starting to put electrons in, we can start changing the energies in these guys. And this is what we see. So in multi-electron atoms, we now know that the order of stability is 1s, then 2s, then 2p, then 3s, 3p, 4s, right? And this is because of electron shielding. The electrons in there change the energies of those orbitals. And this is what's going on here. So on the periodic table, lithium through nitrogen behave, let me start this way. Oxygen and fluorine behave normally. I expect to see sigma lower energy than the pi's, right? These are the 2p's. So for me, this is expected. N2, C2, B2, Li2, these guys are backwards. These are upside down. And so this is just something you need to know and be able to recognize. So for O2 and F2, the sigma and 2pi are backwards, right? Inverse compared to the other ones. And this is due to orbital mixing between these two things. So what's actually happening is that this guy is interacting with this guy. I think that makes this a lie. And what's happening is this guy's becoming less stable, and this guy's becoming more stable. This guy doesn't really move. But what you see then is that, so the pi's aren't really moving, the pi 2p's aren't really moving. This sigma star is lower energy than expected, and this guy's higher. And so that changes the order. And as you get down to O2, the order becomes as we expect. So that orbital mixing effect is less. We don't worry about it. All right, so you need to recognize that for everybody up to nitrogen, pi 2p comes first, and then oxygen and fluorine, it'll be sigma 2p first. All right, I guess let's go ahead and fill out these MO diagrams so we can talk about them. I think that's true. Yeah, it is. All right, so first off, how many electrons? Let's do lithium first. How many electrons? Oh, it's starting with 2s. So this is just the valence, right? The 1s core is down here. When I calculate the number of electrons, we have to use valence electrons only, not total. So how many valence electrons does lithium have? It has 1. Lithium has 1, so dilithium should have 2. So I put them in here. Nice. Should we calculate this stuff as we go? Yeah, let's do it. So what's the bond order? Bond order will be 2 minus 0 divided by 2 is a bond order of 1. So probably what you should do is pause me and go ahead and fill this all out yourself, and then come back and we'll just double check. And it'll also be diamagnetic. So you did it right. Okay. So B2 valence is 3 valence electrons for boron, so it should be at 6. So 2, 4, 6. Bond order is, these guys ignore, so 2 minus 0 divided by 2 is 1, and it is paramagnetic. C2 has 4 valence electrons, so 2 times 4 is 8. 2, 4, 6, 8. Interesting. So 4 minus 0 divided by 2 is 2. Bond order of 2. Expect it to be diamagnetic. So it predicts it would have a double bond character if you had C2. N2, we have 5 times 2 is 10. 2, 4, 6, 8, 10. 6 minus 0 divided by 2 is 3. Triple bond, as expected, and diamagnetic. Now, O2, 6 valence electrons times 2 is 12. So 2, 4, 6, 8. Oh, violation. 12. Oh, yeah, there's all paramagnetic O2. And bond order would be 2, 4 minus 2 is 2 divided 4. Sorry, 4 divided by 2 should be 2. Fluorine has 7 valence electrons. 7 times 2 is 14. 2, 4, 6, 8. I'm following the rules this time. 2, 4, 6, 8, 10, 12. Oh, I broke the rule that time. 14. So let's see. 6 minus 4 divided is 2. 2 divided by 2 is 1. Bond order of 1, as expected, right? Fluorine has a single bond. Nice. And it should be diamagnetic. All right, there we go. Let me see. Oh. Just close your eyes for a second. The catastrophe. Hold on. Come on. There we go. Back up. All right. There we have that. In the notes, I'm going to have to find this. If you look in your notes, though, the bond length. So what happens as the bond order increases, the bond length should decrease, and the bond enthalpy, the strength of the bond, should increase. So nitrogen, with his triple bond, has a bond order of 3. The length is the shortest of all of them, and the bond enthalpy is the highest, as expected. All right, and what should we do this? Yeah, who should have a stronger bond between diboron and dilithium? They both have a bond order of 1, so single bond. Which bond is longer and weaker? Atomic radius decreases up and to the right, so boron is smaller, so the bond length should be shorter, and it is, nice, and the bond strength should be greater. All right, so there's a whole bunch of things we can predict from the information we already know. All right, then we're going to draw the MO diagram for N2. So this time I have not given you the template, so what we have to do is draw out the whole thing. So to begin with, we have to know, do the pi's come first, pi 2p's come first, or the sigma 2p's? N2 is the exception, I would say, so pi comes first. All right, so let's draw this up. So here's 1s. So this will be sigma 1s. This will be sigma star 1s. Then we get this guy, and you can use boxes if you want, or however you want to do it. And this will be 2s, 2s, sigma 2s, sigma star 2s. Let's see if I have enough space here. Here's my 3 p's, my 2 p's. So we said pi is going to come first, then sigma, and it's always pi sigma up here. Nice. All right. Okay, good. So pi 2py, pi 2pz, sigma 2px, pi star 2py, pi star 2pz, sigma star 2px. All right, now we're going to worry about electrons on the outside. I'm not going to. I only want to know the electrons in the middle. Let's switch to red so it really pops. How many total electrons? We're doing total, right? Not just valence for N2. So N has total electrons is 7. So N2 should have 14. Here we go. 2, 4, 6, 8, 10, violation, 12, 14. That is the complete MO diagram for N2. Bond order is total electrons, so total bonding minus anti-bonding divided by 2, 2, 4, 6, 8, 10. 10 minus 4 equals, divided by 2 equals 3. Bond order of 3, like a triple bond, as expected for nitrogen, right? We know the Lewis structure looks like this. Good. And paramagnetic or diamagnetic? It is diamagnetic. Oof. All right, nice work. So we should be able to draw MO diagrams for anybody in the n equals 1 or n equals 2 periods. Coming back here, so we can write these Aufbaus or electron configurations for this. So here, this is what we filled it out already, but let's write it out. I'm going back to black. So the lowest energies here, we're starting with the 2 P's, but I know what comes first. So sigma 1s 2. That means this is like 1s2, except it's not an atomic orbital, it's a molecular orbital. What's next in energy? Sigma star 2. 1s, sorry, 1s 2. Then sigma 2s 2. Then sigma star 2s 2. And now we're here, so who's first? With carbon, we've got, oh, that's a P, miserable thing. Pi's come first. This picture's not as good. Flip back to your picture. Flip back to this one. Make sure you're looking at this. So who do we get next? Now we get sigma 2s. We get the pi 2 P's next. Okay. So I get pi 2p. What we can do is say pi 2p 4. Or, hold on. Different ways to do this. Come on, thing. All right, pi. I'm going to do it this way. We could say pi 2p and put 4 there. Or let's just say we're using the 2py and pi 2pz, and then we'll put a 4. There's different ways you can write this. There'll never be a question about which way is better, but you need to be able to explain that there's 4 electrons in the pi 2p MOs. So let's do O2. O2 would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now we got our pi's. Oh, sigma first. So then we got sigma 2p2. Then we get both pi's are filled. Right, yes, so pi 2py, pi 2pz, 4. Finally made it. And so then we have 2 electrons in the pi star 2py, pi star 2pz, 2. So this is like writing electron configurations, but they're molecular orbital configurations. Kind of a pain, but there you go.